A Brief History of Game AI by Patrick Peterson. The first step towards the development of game AI was Minimax, a method of analyzing game strategy proposed by John von Neumann in 1928. Minimax assumes that both players have perfect knowledge of the game and all future moves. Knowing all moves in advance allows for the best overall choice for the player to be made, whether by maximizing their own score or by minimizing the enemy's. In 1949, Claude Shannon proposed two general strategies for implementing Minimax for chess programs. Type A relies on brute force and calculates every possible future state of the game from the current state. Type B determines which moves are plausible and then only calculates those, as opposed to Type A, which calculates them all. Type A is easy to implement, but is impractical, since the number of states grows exponentially for every new move to calculate. Type B is more reasonable to calculate, but implementing the code to run it is difficult and never works perfectly. In 1951, Alan Turing created TurboChamp, a hand-calculated program that could only calculate one move in advance. Although the program failed to beat its human opponent, Alec Glims, the program could play better than Turing himself, who was a poor chess player. In 1956, Arthur Samuel designed a checkers program that introduced two more advancements: rote learning and learning by generalization. Rote learning means that instead of calculating all the states from scratch every time, the program would instead store a score for states it had already considered, which decreased computation time at the expense of memory. Learning by generalization is the first true implementation of a self-learning AI in games. It allowed the program to make modifications to its own parameters, which in turn allowed it to tune itself over time to gain an intuitive understanding of the game without direct human intervention. In 1957, Alex Bernstein designed a program to play chess which did not use generalized learning, but instead used preset heuristics which were determined by humans. The use of heuristics allows programmers to tell AIs objective facts without making the program learn them itself. In 1958, Alan Newell and Herbert Simon introduced alpha-beta pruning for Minimax, which was the first step towards a Type B implementation. Pruning involves deciding which moves, if any, are objectively poor and then ignoring the entire branch of states which would derive from that move, since they would be a waste of time to calculate. In 1962, Samuel's checkers program played against Robert Neely and won. Neely was a decent player of checkers, and although the program later lost against checkers masters, the fact that the program beat anyone at all sparked an interest in AI research and proved that programs could beat humans. From 1962 onward, AIs became slowly but steadily more powerful. Increasing computational ability and memory, as well as more efficient implementations of existing programs, allowed for AIs to calculate more moves ahead and store more states learned by rote. The addition of quiescence, the emphasizing of important branches of moves, allowed for AIs to capitalize on advantages they would have otherwise missed due to short-sightedness. In 1988, Deep Thought, the predecessor to the now famous Deep Blue, was created by a team headed by Feng-Xiang Xu, and successfully beat chess grandmaster Bent Larsen. Like Deep Thought, most programs until this time still relied heavily on conditions built into the programs by their designers. In 1989, neural networks were introduced with Neurogammon, a program which used neural nets to play backgammon. Neural networks are a programming implementation of organic thought which uses grids of nodes which each have their own logic, using which a computer could accept a game state and produce a move based on past experience. TD Gammon was created in 1992 and was the first powerful implementation of neural networks using reinforcement learning, which allowed the computer to truly teach itself. Instead of trying to approximate an evaluation function derived by humans, the neural network could now score the strength of a state on its own instead of using what humans thought was a good state. Reinforcement learning is similar to human learning in that the program will evaluate the current state of the game and weigh the options it could take based on their likelihood of reward. This allows for the network to learn by playing itself repeatedly, instead of by having humans feed it values for states. As it plays, it learns which moves are superior and which moves are inferior by experience, and modifies the weights of those moves accordingly. The combination of reinforcement learning with previous techniques allowed for large improvements, but the computation time of the network itself was too large for more complicated games. Monte Carlo Go by Bernd Brugmann introduced Monte Carlo algorithms in 1993. Go was far too complex of a game for even the most efficient algorithms to compute, so instead of computing all of the states like before, the Monte Carlo approach says to judge the validity of a branch by testing random moves therein. This combined with rote-learned states allowed for far faster computation times than before. The problem with neural networks was reduced in 1994 with convolutional neural networks. These networks worked different than the previous networks in that they used layers of nodes to represent larger and larger sections of the board for each layer of nodes the inputs go through. This allows the program to find patterns all across the board, as well as to identify rotational and reflective symmetry, which not only increase the power of the algorithm, but also decreases the computation time. In 1997, Deep Blue was the first program to beat a chess grandmaster, Garry Kasparov, using highly streamlined processing with parallel processing and heavily relying on search-limiting techniques like pruning and quiescence. This approach could not be applied to more complicated games without vastly more powerful hardware, which paved the way for convolutional neural networks. In 2006, Remy Calame developed Monte Carlo tree search, a combination of Monte Carlo algorithms and the traditional tree search algorithms. Levente Casas and Saba Savari developed upper confidence bound for trees, which helped further decide which trees of states to evaluate. In 2008, Mogo, using these improvements, defeated the professional Go player Kim Young-won. Although Kim was playing with a handicap, the event spurred further research, similar to how Arthur Samuel's checkers program did in 1962. In 2013, the company DeepMind trained a neural net with reinforcement learning, which had previously been abandoned after the failure to apply the approach of TD Gammon to more complicated games. With more modern hardware and more streamlined software, the technique proved extremely successful. In 2014, Christopher Clark and Amos Storkey introduced the Deep Convolutional Neural Network to game AI, enhancing the pattern finding and problem-solving capabilities of convolutional neural networks by greatly increasing the number of nodes that the network had to work with. This, combined with having been fed a large amount of data from previously played games between humans, allowed the program to finally get a more intuitive grasp on very complicated game states, like in Go. In 2016, AlphaGo was developed by Clark and his team. AlphaGo combined traditional heuristic and supervised learning from human games with reinforcement learning from the AI playing against itself to improve. It also used 3 networks instead of just 1. The first network, called the policy network, was dedicated to deciding which move was the best from a given state. The second network, called the rollout network, was used to implement Monte Carlo tree search by quickly determining which moves might be worth the time to calculate instead of choosing randomly. The third network, called the value network, was used to replace the dictated evaluation functions by training this network to recognize the strength of the current state in the game. These 3 networks, in combination with a massively parallelizable approach and vastly more powerful modern hardware, allowed AlphaGo to beat Go Grandmaster Fan Hui.